Okay, so you have web work due tonight at 6. I want to point out a couple things. So sometimes in these problems you have to, there's some simplification to do first. So be aware of that. So there may be a way to make what you're looking at easier by simplifying using algebra. Okay. Another thing is this cosine of n pi pops up a lot. And if you don't know what that is, you've got to figure out what that is, because that, once you know what that is, then it will make your life a lot simpler. So see that, think what, right? See that, we've been working on this. See that, think what. So just in general, in a word, what is that? In a word, one word, it's a sequence. The first thing we did in this unit, sequence, which is what? A list of values. So you see that, those symbols right there, what does it mean? When you see that, you think what? Write it out so a third grader can understand. And then once you're confident, you'll find out that that's, knowing exactly what that is going to be very useful in doing these problems. There was one more thing. Oh, so we talked about comparison, and I didn't use this. I said we talked about direct comparison and indirect comparison, remember? And what I said indirect comparison was if you look at that sequence and take it out to a really high value of your index, what does your sequence eventually essentially become? So for instance, this one here. So when n gets really, really big, so maybe this is either comparison or indirect comparison. So what do we think? N squared over n to the fourth is essentially the same as 1 over n squared. So is what we have, is it larger or smaller than 1 over n squared? What we have, this whole fraction here. Bigger or smaller than 1 over n squared? Bigger. The numerator is bigger and the denominator is smaller. Those are both both contributing to this effect of making that whole fraction bigger, right? So 1 over n squared we know is convergent, but we have something bigger than a convergent series. Conclusion? Who knows, right? By direct comparison, you can't make a conclusion. You can't say, because it says you have something bigger than 1 over n squared. So then we talked about, okay, so as n gets really big, this thing is essentially 1 over n squared. So when n gets to be a million, a billion, a trillion, this thing is going to be converging on, the sequence is going to be converging on basically 1 over n squared. And because of that, what can we conclude? Convergent, right? Because we know this is a convergent, a p-series that converges. So if this is going to evolve and get essentially to be the same as that in the end, then we would say this one converges as well. So that is another kind of comparison. What are we doing? We're looking at the limit as n gets large, and so I call that indirect comparison, but they're calling that limit comparison. So that's what when you say limit comparison, that's exactly what we did. We took the limit and we compared it to something that you get when you take the limit of that sequence, which is 1 over n squared. So this would not be direct comparison, but it would be indirect comparison, or what they're calling limit comparison, right? You're letting n look at the limit of the sequence as n gets large, and then you reason that this is going to basically be the same as this in the end. So therefore, this will converge as well. Okay, so I just want to point that out. What they mean by limit comparison is what we call indirect comparison. Okay, so tonight at 6, you have to have those done. And then we're going to start new stuff, because we did quite a few ratio test examples last time, so I think we covered that pretty well. We're going to start the new stuff. Oh, and we got our exam this Friday. if I'm going to send an email out for anyone that has conflicts, you can't create a 1.5 hour window between 9 and 11:30. If that's you, reply. You don't have to send me an email. Just look for the email and reply to the one I send. And it'll be the same procedure as before. Show up between 9 and 10, and you have till 11:30 to work. Or you'll have 90 minutes from the time that you come. And I put up I put up a whole slew of 271 Blackboard. If you go to exam prep, I got lots of information to help you study. There's practice of analyzing sequences and series for convergence and divergence. So I think it's Thursday at 7 p.m. I'll put the answers up to those. So right in the same place, just right here, Thursday at 7, the answers for those will appear. But then for that, you're only doing these. So read carefully. Read this whole post very carefully. These are the ones I'm recommending to work on from that PDF. Okay, so it's not all of them. It's just those. Still have a question, Nick?
It's the breakdown of the test similar to the first task or similar to the
No, I think this one, yeah, it's mostly multiple choice and maybe some free response. But I think it's mostly multiple choice, yeah. Okay, other questions? Okay, so let's do what's called power series. Power series. Yeah?
For the test, will we have to lower your sample for knowing you stuff that
Yep, that's going to be on there. Yep, that's the first set of material. I guess that's not in the post, right? Yeah, so so his lectures and the homework that we assigned, which was just, it wasn't much, but a couple problems. Yes, that's fair game for the exam, even though that's not in the post. Thanks for asking that. Okay, other questions? Okay, so let's, before we talk about power series, we should recognize this as our geometric series, right? And so we want to, so in your homework you'll see that, and in the future you'll see lots, these series can be written starting from I equals 0, not I equals 1. Why did we start with I equals 1? Because we were taking a series as what? The sum of the terms of the sequence. And with the sequence, it was very convenient and made sense to call the first term number 1, and the second term number 2, and the third term number 3, right? So that just made it very comfortable and easy. And so that's why we started off. Most of the series we've looked at so far have started at I equals 1. But you can start at anything you want, right? And so what you'll see is lots of series starting at I equals 0. So we got to start getting used to that. So what we're going to do is, what I want you to do is, first of all, I want you to write out what this means so that a third grader can understand. So what are all these scary symbols, right? This big scary expression here is something not so bad. So you're going to write that out. And then, as a result of writing that out, we want to rewrite the summation notation so that I starts with 0. But here's the key. What we put here has to generate the exact, starting from I equals 0, the exact same terms. We want it to be the exact same sum. So if it's the exact same sum, it has to generate the exact same terms. Okay, so first write out what it means. And then you're going to take a look at what you wrote and come up with a way to get those exact same terms, but where I is starting from 0 instead of I starting from 1. And I think you'll find out this is not too difficult if you know what's going on. It's pretty easy. Okay, so first of all, the first task here. When you see this, you think, what? Kevin, did you get it? When you see this, you think what? What does that mean? Not quite. So once we start applying the i's, we're not going to have i's in this anymore, right? Because we're going to start with I equals 1, and then I equals 2, and then I equals 3. Okay. Okay. And what's AR to the 0? Yep. So then AR first. Yeah, there you go. So that's what that thing means, right? I did that just so I could do this. All right, so then the question is, what will we write here? Now, what will what will the new sequence be, so that when we sum up starting from I equals 0, we'll get the exact same sum, the exact same terms? What do you think, Samantha?
AR to the I.
She wants AR to the I. So then AR to the I, starting from 0, will generate the exact same sum as this one did. You should see that, that's right. Okay, so this is what's called shifting the index. What did we do? How did we shift the index? Did we shift it up 1 or down 1? We shifted the index down 1, right? So we start, rather than starting from I equals 1, we're starting from I equals 0. And what happened to the I in the formula then? What happened to every I in the formula? It went up 1, right? So in order for this to maintain the same terms, if you start from a lower I value, then you've got to add 1 to all the i's in the formula, and then you'll have back what you started. Should make sense, right? Yeah.
Why is it referred to as the index rather than the variable?
What is that?
Why is I or N or J
Okay.
referred to as the index instead of the variable?
Instead of the variable. What do you mean by the variable?
Like the independent variable.
What's that?
The independent variable.
We don't have an independent variable here.
Because it's just every phone number, is that why?
Yeah, this is just summing up a list of numbers.
Okay.
Yeah, there's no variable here. In fact, this is I mean, you're talking about exactly what power series is. But there's no variable in these. A is a constant, R is a constant, and then by taking different powers of R, we generate this list, and then we add them together. So there's no independent variable here. Is it okay?
I guess I'm wondering why I isn't called
Well,
independent. Why is I referred to as the index?
that just goes back to sequences, right? So index just keeps track of which one we're talking about.
Okay.
So this is the first one, so I equals 1. This is the second one, so this is where I equals 2. I equals 3. So index is like keeping track, like filing, right? Keeping track of something, indexing it. And it always just marches up by 1 every time. Okay. All right, so a power series. Okay, so that was example of shifting the index. And now we have two ways of writing. This is a new way of writing our geometric series. So this is valid, just as valid as this now. Starting from I equals 0, instead of starting from I equals 1, then it'd be AR to the I. And you get the same exact terms. Okay, so a power series then is of this form. Okay, so C sub I, x to the I. So now I want you to write out what this means. Write out what this means. You see this? You think what? Write it out. Okay, Edmund, what do you think? Did you get it?
I started out with C sub 0.
Yep, C sub 0, good.
Plus C sub 1x.
Okay. Yeah, he nailed it, right? So all you're going to do is replace I with 0. That's your first term. Then replace I with 1. That's your second term. Replace I with 2, and that's your third term. You're going to add them all up. Okay? So here, what's different about this? So we have, what we get is, we get real valued coefficients. So this CI is kind of generic for, there'll be some formula of I, right? So this just could be any formula of I that's going to give you a real number, and it could change from term to term. Okay? So we're going to have real valued coefficients, and then we have an independent variable. So this is new. We have an independent variable, x. Okay, so when you look at this, C0 plus C1x plus C2x squared plus C3x cubed, that should remind you of something. What is that like? What is that? Oh, please, somebody know this. What's that? Polynomial, right? So this, you should be thinking, oh, that's like a polynomial that you've been dealing with your whole calculus and algebra career, right? So it's like a polynomial, but what's different about it? There's something different about it. The fact that it's a series means that it's a polynomial that does what? What do you mean?
It's an infinite.
Yeah, so it's like an infinite polynomial. It has an infinite number of terms. You just keep adding, right? You just keep adding with a higher and higher power of x each time. Okay? So this, what this power series is like, it's like a function that's a polynomial, but the difference is you have an unlimited number of terms. So that's what we mean by a power series. So now we're talking about writing a function as a series, right? So writing a function as a series in this case, and that the series would be, or that function would be like an infinite polynomial, or a polynomial with an infinite number of terms. Okay, and so then this begs a question, right? So what's the important question we want to know? So x now can vary, right? So for every value of x that you put in here, you get a different power series, right? You can put in x equals 2, x equals 0.5, and every time you put in a different x, you get a different power series, giving us kind of like the value of the dependent variable when you added up all the terms. So what's the question that this begs? What question do we want to answer? Yeah, nailed it, right? So for what values of x will the power series converge? Okay? So for what values of x will the power series converge? I mean, that's what this has been all about for the last couple of weeks. We're interested in knowing when these sums add up to something finite. Okay? If it just adds up to infinity or it keeps bouncing around, it's kind of so it's not really useful, or it's kind of more trivial. But when we get an infinite sum that adds up to a finite number, okay, well, that's interesting. So same thing with this. So you have all the tools to do this, but now we just got to think about x as an independent variable. So let's look at an example. Here's one. X to the j over 3/4 j minus 1. So what is the c sub j? Could you define before we start? So remember, so this would be like what? C sub j, x to the j. That's our j goes from 0 to infinity. So what's the c sub j? A couple of you saying 1 over 3/4 j minus 1, right? So in this case, that c sub j is 1 over, this is how we're going to generate the coefficients for the polynomial. The coefficients will be 1 over 3/4 j minus 1. Okay, so what we're going to do is we're going to use the ratio test. We're going to use the ratio test to find the values for which this series converges. So you're experts at the ratio test from Friday and working on your homework, right? What do? The ratio test? Write the first step. Can you write the first step of the ratio test? And so just x is going to just come along like, you just treat it like any number in your formula, but you leave it as x. So how do we start this? Yes.
Aren't there any particular values of C for which the series converges? Or are we only concerned with the values of X?
Because every value of X gives a different series, right? So when you put a value, no, but C doesn't change. C doesn't change. For this power series, this will always be this, right? And then with different values of J, you get the different coefficients.
So like for a particular value for X, C can change.
No. You just have a different based on this formula for this power series, you get a different coefficient for each term. So changing C means you have a new power series. You're changing the power series. What's that? Yeah, so this is the formula for the C for this power series. So C changes with J, right? Every term gets a different C. But if you change the formula for C, you're talking about a different power series. You see?
So here we are finding like the particular values of X in a particular power series.
For this power series, this power series will converge for some values of X and will diverge for other values of X. Yeah.
How do you identify what term in that function is C sub I?
That's what we just said, right? So C sub J is the 1 over 3/4 J minus 1. So the whole thing looks like this.
So it's just the term without the independent variable.
So you're gonna have X to the I or X to the J, and everything else is your C.
Okay.
Did I answer it?
Yeah.
Everything else is gonna be the whole formula that's their coefficient of X to the J is your C. All right, so first step. What's the first step? I got this. Julie, did you get it?
I just have this set up.
Yeah, tell me.
So x to the j plus 1
Yeah?
over 3/4 parentheses j plus 1 and parentheses minus 1 and
Okay.
then all over x to the j over 3/4 j minus 1.
Right, and let's start by just inverting and multiplying. Yeah, perfect. Yeah. So this is the first, and I don't know why I've got I's here now. Sorry. Those should be J's. Okay, those should be J's. It doesn't matter, right? It doesn't. We're making a new sequence, and we're taking the limit of a new sequence, so we could change it to I. It doesn't matter at all. It's just a symbol standing for the index on the sequence. So there's nothing wrong with this. Okay. All right. So this is what you should have wrote, but you might have had J's. Okay. Questions on that? Is that right? So now we do this. We do the same thing as before. Right? So x to the I plus 1 over x to the I is, just you have one more x on the top than the bottom, right? And you're going to left with one more x. And then you have 3/4 I minus 1 over 3/4 I, and that ends up being minus 1/4. Because you have 3/4 times 1 minus 1, it's going to be minus 1/4. Right? 3/4 minus 1 is minus 1/4. Okay, now we're ready to take the limit. What is the limit as I goes to infinity of this? Absolute value of x, right? So this whole thing is 1. This, when you take the limit, that goes to 1, right? We've got the ratio of the leading coefficients, and that's just 1. But x does not care what I does, it's just x, right? So after we take the limit, what we're left with is the absolute value of x. Okay? And so what does the ratio test tell us? When does a series converge according to the ratio test? When your limit is less than 1. Less than 1. Right? So convergence is when whatever you get is less than 1. Well, now what we're getting is a function of x, right? We're gonna have an expression with x in there. And so now this is telling us what values of x will make that power series converge and what values of x will not. So what values of x make the series converge? Between -1 and 1, right? So this ends up being between -1 and 1. What if x were -1 or 1? What would the limit be? Equal to 1, right? The limit would be equal to 1. And what happens in the ratio test when the limit equals 1? Inconclusives. So what we're going to do is we're going to actually let x be 1 and write the power series when x is 1, and we're going to solve that one separately. Okay, so we need to check these separately. And all we need to do is just take -1 and 1, which makes an inconclusive result in the ratio test, put them into the original power series, and then the x's are gone. It's no longer a power series. It's just a series like we've been working on the last week or so. So when we put in x equals -1, what series do we get? What's that, Tom? We get an alternating series, right? Because we'll have -1 to the j over 3/4 j minus 1. So now we have our toolbox, and we have to take our toolbox to this, and what is going to help us solve this? Is it a p-series? Is it a geometric series? Is it alternating? Is it, what are we going to use to analyze this series? -1 to the j over 3/4 j minus 1. So what can we do with this? It's an alternating series, so we could try the alternating series test, which says that the positive part of our series, everything except the alternating part, has to do what? Decrease to 0. As long as it decreases to 0, it can do that as slow or as fast as it wants, and with the alternating effect on it, it'll converge, right? So does 1 over 3/4 j minus 1, as j gets large, does that decrease to 0? As j gets really, really big, 1,000,000, 1,000,000,000, 1,000,000,000,000, will this decrease to 0? The whole thing? Sure, right? That denominator gets very, very big. So the alternating series test tells us this will converge because the 1 over 3/4 j minus 1, it decreases to 0. Because it alternates, that's all we need to say that it will converge, like the alternating harmonic series, right? Just like the alternating harmonic series, same reasoning. Okay, then we try x equals 1. What series do you get when x equals 1? Almost, right? Not quite. When x equals 1, then the denominator just goes away. It's just 1, right? 1 to the j is just 1. So you have 1 over 3/4 j minus 1. Convergent or divergent? And why? So I want you to, can you say convergent or divergent and give good reasoning why? Talk to the person next to you. Go. Does this converge or diverge? And good, solid mathematical reasoning why?
Yeah.
Okay, Hannah, what do you think? Why? She thinks it diverges. Is it a p-series as it is?
It's very close.
It's not a p-series because it's actually what? Like a p-series is strictly, this is the only thing that's a p-series. 1 over j to the p. If there's any other bells, whistles, nooks, crannies than that, it's not a p-series. But it's really, really close to the p-series, right? So in which p-series is it really, really close to? 1. So with a harmonic, right? So it's really, really close to 1 over j to the 1. So what can we do? Compare it. So either direct comparison or maybe limit comparison, right? Like indirect comparison. So can we use direct comparison here? What about the harmonic series? It diverges or converges? Diverges. So to use direct comparison, what would have to be true about this? Every term would have to be larger. Is it larger? Yes, because everything we're doing here in the denominator is making the denominator smaller. We're taking 3/4 of j and we're subtracting 1. So this has a smaller denominator than the harmonic series. Therefore, all the terms are larger. Therefore, diverges by direct comparison, right? Diverges by direct comparison. So if that's what you said, then good job. Okay, so this is that whole fraction. All those terms are greater than the terms of the harmonic series. Yes, ma'am.
Would that be incorrect if you just said comparison to the harmonic series, or do you have to say direct or indirect?
It's good that you know. Yeah, so you should know the difference. You should know the difference. Yeah, just be as thorough as you can, and we should know the difference between those two. Okay, so therefore, we know for sure between 1 and -1 that power series converges, and then also at -1, but not at +1. So we get the whole interval of convergence then is -1 less than or equal to x less than 1. So these are exactly now the values of x for which that power series will converge. If it's not in that, if it's not one of those x values, the series will diverge. Okay? So there's this thing called, so if we graph that, we'd graph it on a number line, it would look like this, right? So we're including -1, but not including 1.
Why is that? Well, I know that.
Okay? And so what we'll have in these intervals is a center. What's the center of this one? 0, and then we'll have, if you think of it as kind of like a flat circle, and so from the center, there is a distance out to the ends of the interval, and so that's like the radius of a circle. So they often talk about this thing as, think of this as this interval kind of as a circle, and so the center of the interval is 0, and the radius of convergence is 1 in this case, because it's how far from 0 out to the ends of the interval. So there's this language that they use, the radius of convergence. Okay, and so then if you ever get to complex numbers, complex analysis, you actually do these problems and you're actually in the three-dimensional plane and you have a center and you truly have a circle. That's your radius, your circle of convergence. Okay? So this is just this is the one-dimensional version of that. It's like you think of that circle as just like flattened into a line. Okay, but they still use this language, even in our case here. The radius being the distance from the center out to the ends, just like it is in a circle. Yeah.
So when we look at the original series, do we not know it's a power series till after the ratio test?
No, it's a power series because it meets this criteria, right? C I x to the I. So we have the C x to the j. That's why it's a power series. We knew it was a power series before we started.
But if you ever end up with, like a variable after the ratio test, it's always a power series. Like instead of that just.
No, it's a power series because the series is of this form: C sub I x to the I. And then yes, when we do the ratio test, we may end up with an x in our result in the ratio test. Does that make sense? Okay. Other questions? All right, so let's take a look at this in GC and see how I'm going to make a function out of this series, and we're going to see what happens between -1 and 1 and outside of that. Okay, so what I've done here is I've done the one we just did and called it f of x. And I said j equals 0 to p, so I can adjust that. And what am I adjusting that value, then what am I looking at? If I'm taking p to be 3, 4, 5, 6, then what am I really looking at? Partial sums, right? Partial sums. And if I take greater and greater partial sums, or partial sums for greater and greater values of p, then what am I essentially doing? Getting better and better approximations for the series, right? The more terms you take, the longer the partial sum, the better approximation it is for the whole sum, right? Every time you add another term, you make that new partial sum closer to the final sum of all infinitely many terms. Okay, so I'm making this into a function, and I want to graph. So I want to graph it for, what did we say? This should be less than or equal to, right? Was that the interval that we found that converged? All right, and I'm going to start at p equals 0. So p equals 0 is, now that's the first partial sum because it's going to be for j equals 0. So let's graph that. And actually, I'm going to graph the whole thing. So does the gray show up? No. Does it show up now? There we go. Okay. So so this is just the first partial sum, and all we do is it's just when j equals 0, we just get what? -1. If you plug j equals 0 in here, all you get is a -1, no matter what x is, right? No matter what x is, you get x equals -1. But every time I take go to the next partial sum, so now I'm going to add the first two terms together. And this is what I get. So this is when j equals 0 and j equals 1, you just have the two terms, right? So let's write that out. So when p equals 1, we'll have x to the 0 over 3/4 times 0 minus 1 plus x to the first over 3/4 times 1 minus 1. So what is that? 1 over, so that was the -1 we got for the first partial sum. And what's this? 3/4 minus 1. That -1/4 x? 3/4, no, -4x. 4/3. Okay, so that's what we're looking at right now. The second partial sum, that's when p equals 1. You're looking at -1 plus -4/3 x, and that's what you get, that line, right? And so when p equals 2, we'll get a quadratic. We'll get the first three terms. So there's the quadratic. We'll get -1 plus -4/3 x plus whatever x squared, right? Whatever the term is for x squared. And so what are we going to expect to see as we make p much larger? What are we going to expect to see? The difference between the blue and the gray. What's going to happen with the blue and what's going to happen with the gray parts of this function? What was the whole point of all this work we did? What's that? No. Definitely not. What was the whole point of all this work we've done the last 20 minutes?
Blue area should be getting smaller, gray area should be getting larger.
Not necessarily getting smaller. Yeah, what does it mean? Converging. What does that mean, converging? I'm not talking about asymptotes. I'm talking about that the whole point of these power series is for some values of x, the series converges. Okay? And so if you pick a value of x, say pick 1/2, you just get a series, right? And is this series going to converge for 1/2 or not? And what does that mean? When x is 1/2, we add all the terms together, we're going to get what? A finite number. That's what a convergent series is. You get a finite number. All right, what about if x equals 3? What's going to happen? Is our series when x is equal to 3, the y value at x equals 3, is that going to sum up to a finite number? No. So we got to think of that for like intervals of x, right? So in the interval from -1 to 1, this power series is going to, all the y values are going to be converging to particular values, and when we're outside of that, the y values will be doing what? Not honing in, right? The more that you add, the worse it gets, right? It's not going to be honing in on particular y values. So let's watch it happen here. So here's the fourth partial sum. So I'm just going to keep adding a term. Every time I click, I'm adding another term to my partial sum. And on the left, it's going haywire, right? It's flipping up and down, up and down. And then on the right side, right of 1, it's just flying up fast. But the blue part of this function, from -1 to 1, is what is honing in on a particular function, right? It's converging on a particular function, but then outside of that interval, all those y values are they're never gonna hone in on a particular y value. They're either gonna, on the left, keep flipping up and down, getting worse and worse, or just keep getting larger and larger on the right. So if we do say p equals something big like 500, takes GC a little time to do that. That's a lot of work. But now we're getting a really good idea of between -1 and 1 what that power series, the function that power series is converging to. But then outside of that, whirling off to infinity for all x values. Okay, does it make sense? Okay, you try. See how this goes. So write this down, and I'm going to take attendance.
Yeah.
There's the first step. So how many more x's do you have on the top? Then on the bottom? 2 more on the top? Okay? And then you have 2i plus 1 factorial over 2i plus 3 factorial. Did you get this? You should have gotten this far at least, okay? And so then how does those factorials simplify?
2y plus 3 and 2y plus 2.
That's right. So what's left is 2i plus 3 and 2i plus 2 in the denominator. Because then after that, you have 2i plus 1 factorial in the denominator, and those go away. So we have that. What's the limit of that? Is it 0 no matter what x is? Yes, the limit is 0 no matter what x is. So what's the interval of convergence? For what values of x does that limit equal to 0? All. So what's happening here is it doesn't matter what x is, you'll always get, so for what values of x is that limit less than 1? Because that's when the ratio test tells us we have convergence. For all values of x, because it doesn't matter what x is, that limit is 0. Yeah?
How did you simplify the exponents to get x squared?
Did you get this step?
Yeah. I got
You agree with this?
Yeah.
So you have 2i plus 3 and 2i plus 1. So how many more x's do you have on the top than on the bottom? Okay, don't pack up. Hold on. So in this case, for this one, it doesn't matter what x is. The c part, the negative 1 to k over 2k plus 1 factorial, heads to 0 so fast that it doesn't matter what x is. So all real numbers x. And so the interval of convergence then is negative infinity to infinity, and then the radius is infinitely wide, because if you thought maybe the center, you could say the center is 0, then the radius would be also an infinite radius for your interval of convergence.